The homepage was fast for months. Then one Tuesday at noon it stopped, the database saturated, and every dashboard turned red at the same second. The cache had not failed. The cache had worked perfectly, right up to the millisecond one popular key expired. And then several thousand requests discovered the absence of that key simultaneously and all went to fetch it. So let's design a distributed cache properly and look at the specific way caching moves a problem rather than removing it. The default pattern is cache aside, and it is the default for good reasons. The application asks the cache. On a hit, it returns. On a miss, it reads the database, writes the value into the cache with a time to live, and returns it. The application owns the logic, so the cache is never in the right path. And if the cache disappears entirely, the system gets slow rather than broken. That last property is worth more than it sounds, because the alternatives give it away. Read through and write through hide the database behind the cache, which is tidier until the cache becomes a component you cannot run without. Cache aside keeps it an accelerator. The time to live is doing something specific here, and it is worth being honest about it. It is not a correctness mechanism. It is a bet on how long you can tolerate being wrong. Every cached value is stale the moment it is written, and the TTL only decides the ceiling on that staleness. Now, the failure. The interesting keys are not evenly popular. One of them, the homepage, the trending item, the pricing table, gets a large share of all traffic. It is written to the cache once with a TTL, and every request thereafter is a hit, which means your database has spent months serving essentially one query per TTL for that key, and it has been sized, tuned, and reasoned about on that basis. Then the TTL elapses. Every request in flight misses at the same instant, and each one does the correct thing. It goes to the database to repopulate. The database now receives, in one burst, the traffic the cache had been absorbing all along. That is the thundering herd, or the cache stampede, and it is a design consequence rather than an accident. The more effective the cache was, the harder the moment it stops. The failure is not caused by the cache being wrong. It is caused by the cache being right for a long time, and then briefly not existing. There are three fixes, and they are not interchangeable. The cheapest is jitter. Instead of a fixed TTL, add a small random offset per key, so a set of keys written together does not expire together. That solves the correlated case and does nothing for the single hot key. For that, you need single flight. On a miss, the first request takes a short lock, fetches, and populates, and everyone else waits briefly for the result rather than launching their own query. One database read instead of thousands, at the cost of a small stall for the waiting requests. The third option avoids the stall entirely. Serve the stale value while refreshing it in the background, so a request never waits on a repopulate at all. That is usually the best experience, and it means deliberately returning data you already know is expired. Which one is right depends on a question only you can answer. Which is worse for this data, being slightly out of date or being slightly slow? One more piece, because caches get bigger. To spread keys across several nodes, the naive approach is to hash the key and take it modulo the number of nodes. That works until the number of nodes changes, and then almost every key maps somewhere new. Adding one node to a cluster invalidates nearly the entire cache at once, which is the stampede again with the whole key space behind it. Consistent hashing fixes it by placing nodes on a ring and giving each key to the next node clockwise. So adding or removing one node only moves that node's share. And there is a commercial reading of all this that is easy to miss. Every cache miss is a database read, and a database sized for a 99% hit rate is a fundamentally different machine from one sized for 90%. The hit rate is not just a performance metric, it is one of the largest levers you have on the bill. That framing, where an architectural decision is really a cost decision wearing a technical hat, is worth taking seriously across a whole system. The Architectural Economics series does exactly that. Idle capacity, egress, storage tiers, and the design choices that quietly set your monthly bill. That is where to go next